Okay, so yesterday I sent you a question to take a look at um, that involved a drug test for high cholesterol. Um, Not that one. That's the one for today. Not that one. Where is it? Oh, there it is, right there. Yeah, right there. Um, and so this one, again, I picked this one because there are no calculations, and so I think this is very likely a type of question you might receive because it doesn't require calculations. And quite honestly, this one is pretty straightforward in terms of what it asks. But and so the reason I picked it was not because it's degree of difficulty, but just because of some of the terms that we have not talked about in a long, long time. Yesterday, we talked about doing a survey with cluster samples or stratified random samples. So today, I thought, well, let's talk about doing an experiment. Um, and this one says, there's a new drug for treating high cholesterol, and they want to compare its effects to one that is already existent or already available on the market. And so the volunteers already have high cholesterol, and they are not currently taking medication. So the first question is, how do you carry out a completely randomized experiment? So you would take all of the volunteers and then just randomly assign them to one of the two treatments. Treatment one is the old drug. Treatment two would be the new drug, for example. And quite honestly, it would be okay for you to include treatment three, which is a placebo or no drug. But the scoring guidelines say that this is enough to get you full credit. But if you added a third treatment, which was a placebo, that would be perfectly fine. So even if you added that here, no problem. And the other thing I want to point out at the end, we have always had this little part at the end, and sometimes I get in a hurry and I would just say compare results. But for this test, you need to give your answer in context. And so rather than just saying compare, that you're going to compare results at the end, you're going to compare what? Well, we're looking at cholesterol levels of the subjects. And so make sure your answer is always in context. Again, I drew this because that's my nature. I'm a visual learner. I see diagrams much better than I write, I think. You could also just describe this in paragraph form. And of course, since you are likely going to be typing your answer, paragraph form makes more sense. But all you need to do is just describe what you see here. So on scratch paper, you may sketch this out and then simply just type what you see. So that's the first part. The second part, I think there was a little bit of a twist in the question because it says describe an experimental design that would improve design A by incorporating blocking. So whatever you came up here, you want to add this notion of blocking. And really that's why I picked this question, so that we could refresh our memory on what is blocking in an experimental design. And blocking simply means that you group subjects because they have a similar characteristic before you divide them into, or before you randomly assign them into treatment groups. And the statement up here, the problem statement, doesn't really say a lot about what characteristic they want you to block on. And so completely open-ended. What you have to do here is simply to pick a factor that plausibly impacts cholesterol level. Now, the problem statement does mention being reduced by exercise. So maybe that's a hint, and you could certainly pick exercise level as a way to block. You could also block the subjects on age or separate them based on age. You could have, I don't know, subjects above 40 and subjects younger than 40, or pick the age, it doesn't matter. You could also pick, separate the subjects by gender. And honestly, since the problem statement says that they already had a history of high cholesterol, you could pick a cholesterol level and put lower level subjects in one group and higher level subjects in another group. It doesn't really matter. The question isn't designed that you pick a certain factor to separate the subjects by, but one that is simply plausible. Now, I would not, separate them by sign of the zodiac or shoe size or college major, or, those things aren't really plausibly linked to affecting your cholesterol level. So pick something that makes sense, and any of these make sense. And I'm sure you could come up with other ones that also make sense. And then the way that looks here is you take the subjects and then you divide them according to whatever factor you're going to block on, whether it's gender or age or whatever. After you separate them into groups, then you randomly assign, and then you would use the same pattern of design in part B as you would in part A. So if you just had two treatments, you would have two treatments here, and then at the end, you're going to compare the cholesterol levels among males and the cholesterol levels among females. What you cannot do at this point is combine all of them back together and compare cholesterol levels among the whole group, because for some reason you thought males would respond differently to females. So you don't want to muddy that back up by putting these results back together. So you're going to say that the old drug seems to help males, but it may not help females, or something like that. Again, the key thing here is, what is blocking? And blocking is simply separating the subjects by some similar characteristic before random assignment into groups. And then the third part, again, it brings up a term that we haven't talked about, and it talks about a double-blind experiment. And the scoring guidelines really are looking for two things in this answer. First of all, that you understand what double-blind means. And then secondly, could it be applied to the experimental design that you picked here? And so double blind simply means that neither the subjects nor those administering the treatments know which treatment's being given. So neither these subjects or these folks here giving out the drug and writing up the results know which treatment a particular patient or a particular subject is receiving. And in this case, you could incorporate a double-blind technique for the subjects and for those administering the test. Interestingly enough, there are some experimental designs, I guess, that you could come up with where double-blind could not be carried out. And if you came up with one of those, and then it would be perfectly okay to say, no, in this case, this experiment could not be carried out in a double-blind fashion. But in this case, these certainly could be carried out that way with no trouble. So I brought this up yesterday, or I threw this out at you yesterday, really just to talk about what is this term notion of blocking in an experiment and what is the notion of double blind in an experiment. So hopefully that'll help you help that be fresh in your mind when you open up the test on Friday. Any questions? Any questions here? I mean, the question is pretty straightforward. We've handled harder ones in class, but I really just wanted to talk about these topics first. Any questions? Make sense?
Yep.
Okay. All right, good. So what I want to talk about today, the one I threw out at you today was that one. It was this one. And yeah. Again, only wanted to refresh your memory on topics that we haven't talked about in a while. And this brings up the notion of what's an outlier. And so wanted to talk again about how do you calculate outliers. Again, if you're going to do calculations, you can certainly make calculations when you're given the data. You can certainly make calculations with a four-function calculator to determine if a particular point is an outlier, or in this case, if there are any outliers. Since you don't have the entire data list, you can't say this particular point is an outlier, but you can determine whether outliers exist in this set of data or not. And so describe the questions talks about, this is statistics for rainfall in Los Angeles for the 117 years beginning in 1877. And you can see there's the mean, the median, standard deviation, standard error, mean, min, max, Q1, and Q3. So all the statistics that you would need in order to determine whether there's an outlier. Now, interestingly enough, the formula for calculating outlier is not here. Okay, it's not on this sheet. So, you know, if you can't remember, then there is nothing wrong with having this set of solutions in a notebook on the table while you're taking the test, and you can flip this if you want, just to refresh your memory, or you can put tabs in your textbook of where certain things are. This year, those techniques are absolutely okay. In a normal year, that would not be permitted. But in any event, just to refresh our memory, an outlier is a point that is more than 1.5 times the IQR above Q3 or below Q1. And you know, you might recall, just visualize in your mind box plot. Q1 and Q3 are on either end of the box. The box contains 50% of the data. Outside the box to the low side is 25% of the data, and outside the box to the high side is the remaining 25% of the data. And so part A, we just we define how to describe an outlier. And then essentially the method we're going to use here is we're going to calculate this quantity Q1 minus 1.5 times the IQR and Q3 plus that. And if there is a value smaller than the min, I'm sorry, if this value is greater than the min, at least the minimum value is an outlier. There may be others. Or if the maximum value is greater than this value, then there's an outlier to the right. So that's our process. And then the arithmetic is really, really straightforward. IQR is just the difference between Q1 and Q3. and that value is 9.57. Times that gives us a value of 14.355. Then we calculate these differences. The value that the boundary for the IQR or for the outlier on the low side is negative 4.675. So obviously there are no outliers on the low side because it's impossible to have negative rainfall. So on the low side, there are no outliers. But when we calculate this value Q3 plus 1.5 times IQR, it's 33.6, which is less than the max. And so what that tells us is that there is at least one outlier on the high side. And you know what this max point is, but there's a pretty big distance. There's a pretty big amount of rainfall between 33.6 and 38.2 inches. So there are possibly more than one outlier. So our answer can only be no outliers on the low side, but there's at least one on the high side. There could be more. Since we don't have the data in front of us, there could be more. So that's the best way to answer part B. And then question C, again, is kind of a no calculation answer, but it's really a powerful one. If there was a particular year, or a reporter said that there were only 10 inches in a particular year, was the reporter, what would we say about the reporter's statement? Well, the definition of Q1 is that it cuts off the first 25% of data. And so Q1 being at 9.6 or 9.7 inches, it means that in 25% of the 117 years, so what is that, almost 30 years, there was rainfall less than 0.6, so certainly less than 10 inches as well. So we would respond to the reporter and say that 25% of the years there's been less than 10 inches of rain. That's not particularly unusual at all. And so we would just say, hey, that's fake news. You know, go report with the facts, man. That one, pretty straightforward. And again, I'm really not picking these because I think they're particularly hard. I'm picking them because I just want to refresh your memory of topics that we haven't discussed in a long time, just to refresh your memory. Do I think it's likely that you'll see something like that? Yes, I do. I really do. This is a pretty simple calculation. You can do it with the 4-function calculator. I think it's pretty likely. Now, I will also say this, that you do not have to use this 1.5 times IQR method. Remember in class, we talked about what if the data were normally distributed and we had a mean and standard deviation. Is there a way to classify or quantify an outlier? And you notice that the data that we're given includes the mean and the standard deviation. And so you could say, based on using this analysis, we did this in class, that an outlier based on this ratio or this formula, I guess, an outlier is more than 2.7 standard deviations away from the mean. And if you didn't remember that, you could say, hey, an outlier is greater than 3 standard deviations away. I mean, we've talked about a point that is 3 standard deviations from the mean is really unusual. There is no, this is not a universal constant like the speed of light where everybody agrees on what's the definition of an outlier. The 1.5 times IQR rule is a good one. It is well known and well used, and I mean, from the first time I took statistics, I remember talking about this. So it is a good rule of thumb, but it's not the only one. So if you want, you could say an outlier is more than 3 standard deviations away or more than 2.7. I think the reader is going to be perfectly happy with either one of those approaches. But this one is certainly the most quantifiable, and I think you'll find it in just about every textbook. I know it's very commonplace. So the question says, describe a procedure. If you want to go with the mean and standard deviation, that's perfectly okay. There's nothing at all wrong with that either. Okay. And so that's it for today's question. It's pretty straightforward. I went ahead and wrote this one out ahead of time just because there's so much writing. I didn't want to spend a lot of time watching me write. So I went ahead and wrote it out. I will kind of give you a preview of the question I'm going to ask you to think about for today or afterwards. It really combines several things that we've talked about. And so I think this is a really, really good question. And also it involves some of Einstein's theories. So I thought that's really cool too. But he came up with this idea that space is curved by gravity, and the amount of curvature is depicted, or he gave the quantity a name, gamma, and he said it was equal to 1. Well, Newtonian theory, Newton's said this value obviously is 0 because with Newtonian physics, space doesn't bend, and so that value would obviously be 0. So since Einstein published his theories in 1915, scientists have been trying to measure that value, and here's some data. Notice the axis here is from earliest to most recent. So these are the original or the early scientific studies, and these are the ones that are more recent. And so the question again doesn't really ask you to do a lot of calculations. It just asks you to describe what you see. And you'll notice that the data is given in terms of a confidence interval where the dot represents the estimate, the point estimate. That's the value that they obtained in the study. And because there's variation in everything, they calculated this confidence interval. And so the margin of error is listed by the brackets on the top and bottom. And so the question is about interpreting what these confidence intervals mean. And again, I thought it was a good combination of interpreting graphical data as well as understanding what a confidence interval is. So I'll let you think about that one, and then we'll talk about it first thing tomorrow. So unless you guys have any particular questions, we'll call it quits for the day. Let's see, I could encourage you again to, if you haven't watched the link to the video I sent about top 10 things to before the test, now's a good time to do that. I will warn you, it's about an hour long, so be prepared. But again, all of those things that those guys talk about are very, very helpful, and it's often good to hear it from somebody other than just me. So I'll remind you to do that. Also, you know, I'm not a big fan of cramming for a test. But if you wanted to go through your binder or your textbook and just kind of organize your notes in such a way you could easily get to them if you needed to remember something, then that's a really good way to kind of refresh your memory, jog your memory about things we talked about at the beginning of the year. Might be a helpful way to prepare for the test. Unless you got questions, I'll plan to see you tomorrow.
All righty. See ya.
All right. Have a good one.
Bye.
Bye-bye.